Okay, there are two pre-labs that are going to be due on Monday, April 6th. One of them had to do with the flow of blood through the heart, and then the other one had to do with answering questions using the Wiggers diagram, plus some calculations. So hopefully you've already filled out the pre-lab, or both of them, and now let's go over the answers. The first pre-lab we're going to go over has to do with the flow of blood through the heart. And they wanted you to start with the three vessels that are bringing blood into the right atrium. So they show two of them on this picture. There's a vessel here and a vessel here. So we're going to start with the superior vena cava, letter A, the inferior vena cava, which was letter R, plus also there's the coronary sinus, which is not pictured on this diagram, but coronary sinus was letter P. So A, R, and P. All three vessels bring the oxygen-poor blood into the right atrium, so that's number 2. Number 2 is right atrium, letter H. And then whenever the right atrium contracts, blood passes through the tricuspid valve, which is letter K, that's number 3, into the right ventricle, which is letter B. And then whenever the ventricle contracts, blood pushes up past the pulmonary semilunar valve, which is letter F, into the pulmonary trunk, which is letter N. And then the pulmonary trunk leads to pulmonary arteries. Pulmonary arteries lead to pulmonary veins. So the pulmonary veins in the lungs lead to the pulmonary capillaries in the lungs, which is letter E. So number 8 is E, capillaries in the lungs. And then whenever the blood leaves the capillaries of the lungs, that go through letter S, the pulmonary veins. Pulmonary veins lead to letter O, which is going to be the left atrium. And then the atria contracts. Blood passes through the mitral or bicuspid valve, letter D, that's number 11, into the left ventricle, which is letter M, that's number 12. And then the ventricle contracts. Blood goes up past the aortic semilunar valve, which is letter T, into the aorta systemic capillary. So aorta is first, letter J, and then we have systemic arteries, which is letter I. Now whether it goes up into the neck and head, or if it comes down or into the arm, or goes down into the abdomen, either way. Systemic arteries lead to systemic arterioles, which are smaller blood vessels, and then systemic arterioles lead to systemic capillaries. And then we have another exchange of nutrients and gases. Systemic capillaries lead to systemic venules, which is letter U. Systemic venules lead to systemic veins, which is letter F. And now we're back at the beginning, because the systemic veins would be the coronary sinus, inferior vena cava, and the superior vena cava. And the last part of this case study or the pre-lab, it asks you where do gas exchange occur, or where does gas exchange occur? Well, it occurs in the capillaries of the lungs, which is letter E, and then also the systemic capillaries, which is letter C. So that was everything on the first pre-lab. This picture shows you the Wiggers diagram, and it's separated into an ECG at the top, and then in the middle it's talking about pressure inside of the aorta and the left ventricular pressure, and then the very bottom is talking about the volume inside of the left ventricle. We're going to focus on this on the bottom, and we're going to answer these questions because it asks you what is the end diastolic volume, what is the end systolic volume, and then what is the stroke volume, and then also they want you to figure out the cardiac output. All right, so we're going to do some calculations. Whenever we're looking at filling inside of the left ventricle, it starts right here. So we have filling of the left ventricle, and then we have atrial systole, and that fills the ventricle to the very tip top. And then right before the ventricle contracts, right before the ventricular aortic semilunar valve opens, it's going to be the end diastolic volume. So right here is the end diastolic volume. That reading would be 135 milliliters. Again, I have to draw with my fingers, so forgive me if it looks real cavemanish, even worse than normal. So 135 milliliters, that would be the end diastolic volume. And then if we follow the picture, whenever the ventricle contracts, then blood is leaving, so the volume's going down, going down, going down. Then finally the volume bottoms out. And then the semilunar valves close. And then right before the atrioventricular valves open, there's still a little bit of blood left inside of the ventricle, and that would give me the end systolic volume. So if we look that over here, end systolic volume would be 65 milliliters. All right, so the end systolic volume is 65 milliliters. Well, stroke volume. Stroke volume is the amount of blood that is ejected during one contraction or whenever the ventricle goes into systole. So you take the end diastolic volume and you subtract the end systolic volume. So you take the end diastolic volume and you subtract the end systolic volume. I'm going to do it old school style. We're going to do it like this. 70. So the stroke volume in this picture is 70 milliliters per beat. And that's letter C. And then it wants us to figure out what is the cardiac output. Well, cardiac output is, it equals to the heart rate times the stroke volume. So the heart rate, they tell us, is 75 beats per minute. And we're going to multiply it by the stroke volume, which is 70 milliliters. So you take 70, multiply by 75, you get 5,250 milliliters per minute. But then you need to look at the question. Are we asking for the cardiac output in milliliters or liters? Typically, the cardiac output is read as liters. So how do we change 5,250 milliliters into liters? You take the decimal point and you move it to the left 3 spaces. So basically, the cardiac output in this diagram is 5.3 liters per minute. All right, let's read this second question. It says, Miguel is a 25-year-old jogger with a target heart rate of 125 beats per minute. His resting heart pulse is 70 beats per minute. His blood volume is about 6.8 liters. At rest, his cardiac output is 6.3 liters per minute. The first thing they want us to find is what is his stroke volume. Well, what is the formula that we know for stroke volume? Well, on the previous question, we figured out his end diastolic volume and end systolic volume to create the stroke volume, but we don't have that information. What we have is his cardiac output. So right here is his cardiac output. So cardiac output is equal to stroke volume times heart rate. Well, we know the cardiac output is 6.3. We're trying to find out what the stroke volume is, and then his heart rate is 70 beats per minute. So how do we solve for the stroke volume? You take 6.3 and you divide it by 70, and that will give you his stroke volume, which is going to be 90 milliliters, because the stroke volume will be in milliliters, not in liters. Now letter B is a little tricky. They want you to figure out what his end diastolic and end systolic volume would be. So far all we know is his stroke volume, which is 90. So stroke volume equals the end diastolic volume subtracting the end systolic volume. And all that we know for sure is his stroke volume, which is 90. All right, we're going to figure out his end diastolic, which is how much blood is in the ventricle right before it contracts. But let's look at the end systolic volume for a second. We're going to assume what the average is. And the average end systolic volume is 35 milliliters. We're not going to change that any. So if we know what the end systolic volume should be around, and we know what his stroke volume is, then we can solve for the end diastolic volume by adding 35 to 90. So 125 milliliters is the end diastolic volume, and 35 milliliters would be the end systolic volume. This next question is asking, during his workout, his heart rate increases to 125 beats per minute, his cardiac output to 12,500 milliliters per minute, and would you expect his stroke volume, his end diastolic volume, and his end systolic volume to change with exercise? So this is just a yes or no question. Would you expect all that to change? Well, if the heart rate goes up, then definitely the stroke volume goes up. And if the stroke volume goes up, then so does the cardiac output. So that is a definite yes. We would expect his stroke volume, end diastolic volume, and end systolic volume to change with exercise. It just allows for the blood to pump, or the heart to pump more blood through the cardiovascular system to deliver more oxygen to those places that need it. All right, this next question says, atropine inhibits parasympathetic activity. So I'm going to draw a little arrow down, parasympathetic, of the heart, and discuss the effects of atropine on the heart and describe common expected side effects as a result of its action on the heart. Well, the parasympathetic nervous system, is it in control most of the time with the heart? It is, because it's in control of your resting and digesting system. Now, typically, the sympathetic nervous system is in control. However, the parasympathetic moves in to slow it down. If we didn't have the parasympathetic nervous system in place, then our heart rate would be set at 90, which is too high. So the parasympathetic nervous system moves in, it hyperpolarizes the SA node, and it slows the heart rate down. So if atropine inhibits the parasympathetic activity, then atropine would cause the heart rate to go up, would cause the cardiac output to go up, would cause the stroke volume to go up. All right, and then this question, if the stroke volume of the left ventricle is 65 milliliters per beat, and the stroke volume of the right ventricle is 68 milliliters per beat. God, that looks horrible. Anyway, what does that mean? What will happen to the relative distribution of blood in the systemic and the pulmonary circulation after 15 beats? Well, if we have 65 milliliters leaving the left ventricle, and where does blood go after the left ventricle? It goes into the systemic circuit, right? It goes into the aorta and the systemic arteries. The blood that's leaving the right ventricle goes into the pulmonary circuit. That's the blood that's going to the lungs. So if we have 68 milliliters of blood going into the lungs and only 65 milliliters of blood that's leaving the heart going into the systemic system, that means there's about 3 milliliters of blood that's staying in the pulmonary system compared to in the systemic circuit. So after 15 beats, we're going to have whatever 3 times 15 is, 45 milliliters of excess fluid inside of the lungs. So it creates a pulmonary edema. The case study from today has to do with somebody with mitral valve prolapse, or they have something wrong with the bicuspid valve. And it's allowing blood to back up into the left atrium. Well, if blood backs up in the left atrium, then there's going to be blood that's hanging around in the pulmonary circuit, and it increases the fluid leaving the pulmonary capillaries because it raises the pulmonary capillary pressure, forces more fluid out, which is going to then separate the alveolus from the pulmonary capillaries, going to decrease the amount of oxygen reaching the pulmonary capillaries. So that's the problem with pulmonary edema. All right. If you have any questions about the prelab, please let me know. But the questions from both prelabs, you're going to have 2 quizzes that are going to be due on the following week, which is going to be Monday, April 13th. So Monday, April 13th, there are going to be 2 quizzes, one over the first prelab and one over this prelab.